Today's lesson is on trig functions and the right triangle. More specifically, SOHCAHTOA, where sine of an angle, which we're going to put here is our angle right there, is equal to the opposite over the hypotenuse. In a right triangle, we're going to make this side B known as the opposite because it is opposite that angle. We're going to have the hypotenuse be the longest leg on always opposite the right angle. We also have cosine of theta equaling adjacent over hypotenuse. Here's the adjacent. It is the side that is not the hypotenuse that's connected to the vertex of the angle. And then finally we have tangent of theta equaling opposite, oops, have a little technical difficulty there, opposite over adjacent. What we're trying to understand is the following. If we look at it as a function box, and inside the trig function, which is what you write right here, this part right here, which I'm scribbling in, your argument, you need to put in an angle. You need to input some form of an angle measurement. It could be in degrees, which I have down here at 20 degrees. It could be in radians, trig function of, let's say, pi over 4. But you need to put in an angle. And what it's going to do is it's going to give you a specific ratio. And it's not just any ratio, it's a ratio of two sides of a right triangle. And the question is, what two sides? Well, that's what is determined when you pick your trig function. Are you looking at the ratio of opposite to hypotenuse? Then you want to use sine. Are you looking at the ratio of adjacent versus hypotenuse? Then you have to choose cosine. If you're going to do tangent, then you're looking at opposite over adjacent. Now in these cases, our goal is we will give you the angle and you will get the ratio. If at some point in the near future, and I do mean near future, you will be needing the angle because you have two sides, then that would be considered the inverse. What we're going to focus on using GeoGebra here is I have a triangle that could be adjusted to any angle, and I can also stretch it out to any length. The reason trig works is really this simple. Let me close this up. I shouldn't need the tool anymore. Is that if you have a unit circle, and I would superimpose it on the triangle, please note that there would be a point on the triangle. Fortunately, I'm going to have my notations off, so I'm going to have pointed with my little arrow. So right there at A prime. That point is on the unit circle. It has its own set of coordinates. That would be the cosine of 25 degrees, sine of 25 degrees. What I'm doing is I can stretch this out as short or as long as I want. And the ratio between side B right there and side C, which is right there, the opposite B to the hypotenuse C will be the same no matter if I make B and C much smaller or much larger. And to demonstrate that, I'm going to give you a triangle table. In the bottom corner, I have my results. Here's B. This length right now is 2.615. That's what's telling me in the table. C, down here at the bottom, is 6.188. That's the ratio right here by C. Sorry, that's the length. And I'm telling you that is going to be the same proportion as if B prime, which is right here in the middle, oops, got rid of that on the screen, B prime is equal to 0.423, and C prime, which is always 1 because that's on the unit circle, which always has a radius of 1. To prove that to you, I am going to now hit the trig table because trig says sine will always be B is to C, But that would also be the same as B prime is to C prime, which is right here. And what you're saying is, if you divide 0.423 by 1, 0.423 by 1, you get 0.423. But if you would have chosen to choose 2.615 and divide it by 6.188, you also get 0.423. Which is saying that no matter how far out I go on the triangle, notice here, down here, notice right there, no matter how far out I go, left or right, as the triangle increases, the ratio between B to C is always the same. Why? Because the angle never changes. Yes, if I adjust the angle, then the numbers down here also change. But, oops, that's almost too big of a triangle, it's off the screen. But if I pull it back in, once I've determined my angle, in this case 47 degrees, cosine, the adjacent, which is right here, to the hypotenuse, is always going to be 0.682. It doesn't matter if it's 2.953 divided by 4.329, or if it's 0.682 divided by 1. It always is the same ratio. Doesn't matter if I move tangent to make it even really small. Let's make it down to 12 degrees. If I look at B, which is right here, 0.628, and I divide that by A, which is now 2.953, if I take this number divided by that number, I will get 0.213, which is always the same ratio as if I took this B prime is to A prime. The key to the lesson is trig functions have to maintain a proper ratio in a right triangle throughout the whole time.